go through there and set everybody who can do the post-lab based on attendance. I missed a couple of names. People emailed me that I should have been able to access it, couldn't. If you weren't here, you can do the pre-lab. But the post-lab, you have to come and actually do the procedure to do the post-lab. I might be able to do makeup labs later this semester, but if you have a legitimate excuse for missing lab, the pre-lab can count as your lab. Or I'll come up with some makeup lab time later in the semester, and then you can actually make it up. But that's a little bit iffy. But if you just miss lab, it helps your grade to at least do the pre-lab. The labs boost your grade a lot. That 25% helps a lot by the end of the semester. So do catch lab. I'm going to go on, and we'll go back to doing molds where I left off last time. I did upload another PowerPoint, so maybe it's in the Word file. Oh, did everybody get a periodic table coming in? It'll just help if I have to keep going back to the periodic table. Go ahead and grab one. There might be scribbled notes on it. Our printer's down upstairs, so I'll scramble around to remember I can get it. I'll work my way back up to doing things with molds. Let me just do some examples like this. How much does this weigh in EMU? Alright, I do it like this. There's only one carbon here. I'll remind you, for some reason we don't put the ones, but when there's nothing there, that means a 1. There's 1 carbon, 1 hydrogen, 3 Cls, multiply that. Look at carbon and you'll see 12.01. So 1 carbon weighs 12.01 atomic mass units. It also means 1 carbon is 12.01 grams per mole. It literally means both those things simultaneously. When we get to doing some math, I'll tell you to do it like this. It's a better way of writing it. But AMU shows up here and then it just goes away for the rest of the semester. This is really how we use this chart, grams per mole. What do you see for hydrogen? Everybody look at hydrogen. 1.01. Chlorine. It's on the right, kind of low. What is it? And we just add them up. 12.01, 1.01. 3 times 35.45. 35.45 times 3. This is multiplication division. This is infinitely correct. So I'm going to keep 4 significant digits. My calculator says 3, 5, but I'm going to turn that 3 into a 4. And now I'm going to add them up. Maybe I can do it in my head. I'm already lost. 106.4. So it's 2 there, 4 there, 6, 7, 8, 9. 129.42. All right. Did I do that right? One more thing. Now that I'm adding, it's 2 after the decimal, 2 after the decimal, 1 after the decimal. So really, I'm just keeping that. So it's 129.4, and that's 129.4 AMU, or equivalently, 29.4 grams per mole. And like I said, you want to write that as 129.4 grams is 1 mole. You with me? Just add it up straight off the periodic table. Just write some of these down. So this one, C9H8O4, C9H8O4. What does it say for oxygen?
16.
Definitely not doing that in my head. This will be 8.08. 32, 64, this will be 64. Add them up, 9 and 8 is 17. Four significant figures, 3, 4, 3. So I do keep all of those. 2 after the decimal. And again, AMU is perfectly legit, but really, grams per mole. Kind of after today, or maybe I'll do one of those on the test. The only other place you're ever going to see AMU is on that ACS test at the end of the semester. We're interested in grams per mole. The AMU is really a physicist's world. Clear. So we'll do one more. H18O2. I should erase those. 18. 2 after the decimal, so, 1 after the decimal. 17, 10. But really, we're going with 206.2 grams per mole. Are you with me? Can't put lost you yet. I guess I'll do this one too. Just to thoroughly bore you. So now I've got nitrogen in there. There's 8 of these, 9. Oxygen, there's 2. That's a 2. 1 nitrogen. Nitrogen is 14.1 on the periodic table. This will be 9.09. 2 times 16 is 32. 14.01. I think I did that right. So, grams per mole is really what. Okay. Now what we do. When we were doing ionic compounds, I would have said sodium and chlorine. What's the charge on sodium? And you'd say +1. What's the charge on chlorine? And I'd say -1. And I'll remind you again, if it was +2, I would actually put a 2 there with the plus. And if it was -2, I'd put a 2 there. Again, we omit the 1. I don't know why we do that. But it's just a plus and a minus there. I will sometimes put a 1 there, but that's just my mistake. And then I'd go, okay, what's the formula for this? And you would go positive and negative need to balance. So the formula for this is NaCl. All right. So first, those first few that I did, not the NaCl, compared to the NaCl, what's the difference between these and this? That's a review. 2 different types of compounds we talk about. So what are all of these? These are covalent. This is ionic. And let me clarify. I'll use this one just because it's small and easy to draw. That one, if I drew it out, you would see these covalent bonds. That's the molecule we're talking about when we say CHCl. And if you had a big sample of these, you'd have this individual thing, and you would have another one of those, another one of those. You had a beaker full of this, you just have a ton of these little units. But if you have this, what you have is Na plus Cl minus, Na plus Cl minus, maybe off to hundreds of thousands. Cl minus, Na plus, Cl minus, Na plus, way out. Let me do one more row. So you've got alternating out this way, alternating down this way, and then you see this Na, there'll be a Cl here, then an Na and a Cl and an Na. These come in chunks like this. They don't look like this. If you dumped a bunch of table salt out and looked real close, you'd see little grains of it. They say this size, and another one that's bigger, and then another little tiny one. But they're this array. This is called the crystal lattice, and these are called molecules. That's why we call these molecules, and we don't call these molecules. These are in a lattice. So really, when we're doing the covalent compounds, this is the formula. It's these units we're talking about, the CHCl3. And when it's these, it's really a ratio of ions there. Don't overthink that. If I said I had, what's the charge on Mg? And what's the charge on F? It's -1. If I said, what's the formula for that? Well, we keep NaCl over here. And I said, okay, so what's the formula for that? You need 2 of these to balance the charge, so it's MgF2. And don't overthink this, it works exactly the same way as these do. It's just, I just want to emphasize, that's a ratio. 1 to 1 is the ratio of Na to Cl. MgF2, for every 1 Mg, there's 2 Fs. Exactly how to draw that gets a little nebulous, but here's the point. So we just calculated, you could call it the molecular mass. For ions, I think we have to call it formula mass because they're not molecules. I'm not real picky about that nomenclature because it's just about context. But if you wanted to calculate the grams per mole or the AMU of this, you would go Na1Cl1. So it looks exactly the same when the rubber hits the road. But this is really a ratio to each other because these fit in one big crystal, but they're still 1 to 1. What is Na? What is it? Can't hear you. And Cl? 35. I know some of these. I did that right. 58.54 grams per mole. Or I could write AMU. So that part works exactly the same, despite the fact that they're fairly different things. As long as you got the ratio, which is what you have, when you're looking at the formula for ionic compounds, as long as you have that ratio, it works out. And here you're denoting the individual molecules by that formula. And ultimately, it is the ratio either way. I guess you have to think about it a little bit, but it's still the ratio in the sample. Okay. How did you know just by looking the difference between those and those? How could you know just by looking that these are ionic and these are covalent? You get questions like this. I think I have some like this on D2L. These are all blank, and these are I'll say some. What are the blanks? Yes. These are all nonmetals. If you look at the top left triangle where all the nonmetals are, you got to include hydrogen on the top left. But that top right triangle plus hydrogen, these are all carbon, hydrogen, oxygen, and nitrogen are all in that top right triangle where the nonmetals are. Hydrogen too, but it just goes in there. These consist of, these are in that top right triangle, but this is a metal. far to the left on the periodic table. So these are made up of metals and nonmetals. These are made up of nothing but nonmetals. How about this? So what's the formula mass for Ca3PO4? Definitely just three of these. Got the P and the O. How many P's and how many O's are in that formula?
30.97.
Say again?
30.97 for P.
Oh.
Oh.
I have three of the calciums. How many P's do I have? Two. You do. When you see something in parentheses like that, I'll draw this too. I won't try to draw the crystal lattice, but just realize it's got a Ca, a Ca, a Ca. There's three of those. And there's a PO4 and a PO4. There's two of these. That's what that two outside the parentheses is telling us. So once I've got them all tagged up here, now you can count them correctly. We've got four oxygens, so we've got 8 oxygens. And we've got one phosphorus, so we've got 2 phosphorus. If you can do that correctly, the rest of it is... Okay, so now tell me the masses of... What's the mass of calcium?
1.08.
And phosphorus, top right.
30.97.
And oxygen is 16. So if you add that up, you'll get the formula weight. I forgive you for saying molecular mass. I'll say it 20 times. My phone is dying, so I have to use this thing, and I'm not used to it. 40.08. 8. Infinite significant figures 4, so really I just going to keep that. If you're not careful with all that, you're still going to end up with a decent answer when you do these. 30.97 times 2. 94. I think I did that right, but adding that up, and I'm just going to say grams per mole now. 1 after the decimal, 2 after the decimal, 1 after the decimal. So really, I guess I'll just keep it that to be proper. Now I'm going to pick up where I left off. I'm rephrasing this. This is So you'll have to read these and sort of learn how to pick out the phrasing. But I'm rephrasing this as, if I have 4.7 grams of potassium, which is K, many moles spell that. So I'm phrasing this the way I was phrasing those the other day. This says, according to, usually the first sentence of these is a throwaway sentence. According to nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams, period. What is the estimated average requirement of potassium in moles? But that's the same thing. It's just telling you to convert 4.7 grams of potassium to however many moles of potassium 4.7 is. See what I'm saying? So using these to practice, you're going to have to rephrase them the way I do. But it's good practice just to see that it's the exact same question. All right. You start a question like this. Numerical value, unit, label. And I'm just going to put that over 1. And let me point out numerical value, unit, label. How many? That's asking for a numerical value, unit, label. You see what I'm doing? All right. Numerical value, unit, label. If I just write that down, then I know I'm going to need grams of K down here. And since it ends in moles, I know I'm going to need moles of K over here. Because it says how many moles of potassium. I can go ahead and write that, do that to say there's got to be a numerical value there. So that tells me I need moles of K there. Okay, if you look on the periodic table, what do you see for K? 39 point what?
39.0.
That's moles per liter. And I'm going to tell you to go ahead and go 39.10 moles is 1 liter. And this one is exact. It's infinitely accurate. So we don't even look at that for significant figures. But notice, this has, no, moles per liter. Moles per gram. I don't think we're going to get to moles per liter today. All right. Any more mistakes? All right. Grams per mole. Sorry. That's what I should have written down. This is what's on the periodic table. Grams per mole. Skipped ahead to moles per liter. This is sort of the long form of what the periodic table tells you. 39.10 grams of potassium is 1 mole of potassium. See that? This is what I got off the periodic table, and the rest I kind of filled in. Grams per mole, numerical value, unit, label, numerical value, unit, label. Now we're ready to do this. But notice we've got moles on top and grams on bottom here, grams on top here, and moles on bottom here. I'm going to flip it. I'm going to take everything on top and move it to the bottom, and everything on the bottom and move it to the top. 1. And the rest you just calculate. 2 significant figures, 4 significant figures. This little 1 that I stick here is infinitely exact. This is infinitely exact. So it's 2 significant figures and 4 significant figures. 4.7 divided by 39. My calculator says for my numerical value, 2 significant figures, 4. So I'm keeping those 2. So the answer is 0.12 mole. That's 100% correct, but you could put it in standard scientific notation by going 1.2 times 10 to the negative 1. On a test, one of those two will be there for you to pick, not both, because they're both correct.
And did you decide on those figures?
Two here, there's 4 numbers here. There's a number there, a number there, a number there, a number there. These are infinitely exact. This is 1.0000 out to infinity. So is this, 1.000 out to infinity. So those are, and we want to keep the smallest number of significant figures when we give our answer. So those definitely aren't the smallest. So we're using the same rule we used before. It's just those are infinite, so those definitely aren't the smallest. Here we have 2 significant figures. Here we have 4, so our answer needs to be in 2. So I'll write down everything my calculator gives me, and then I underline the 2 I'm keeping. I do look out here to see if I'm going to round, but that's a 0, so I'm not rounding the 2.
Thank you.
Yep. Everybody with me? There's a check you're learning. Yeah, I'll do this one. This is 3.3, check your learning. Just another example. I'll phrase it my way. A liter of air contains 9.2 times 10 to the negative 4 moles of argon. Let me write that down. AR is argon. What is the mass of argon in a liter? But mass is going to be grams here. The question says, the liter of air contains 9.2 times 10 to the negative 4 moles of argon. What is the mass of argon in a liter of air? But that's essentially, it's just asking it this simple. If you read that question, just read through it and realize that's what it's asking. I rephrased it. And they didn't say grams specifically, they said mass. So don't let all this rephrasing throw you off. Be able to read something that's phrased the way they like it. This is ultimately the question you're asked for. And again, notice, numerical value, unit, label. Numerical value that you're asked for, unit, label. I can go ahead and go grams of argon, because I know that's where I'm going. And I'm going to go over here and go 9.2 times 10 to the negative 4 over 1 of unit label. Okay, I'm in moles. I'm trying to get to grams. Moles needs to cancel, and grams needs to survive. So I know it's this, moles of argon over grams of argon. And now I just need the numerical values that go in here. Look on the periodic table, what do you see for argon? It's on the right side.
39.95.
Grams per mole is what it means, not moles per liter. And I would have you go ahead and do this. Grams of argon to 1 mole of argon. And that's what I'm using here. And it turns out I don't have to flip it this time. It's got grams on top and some moles on bottom. That's what I want. So the 39.95 grams goes up here. And the magic 1 goes down there. These two ones are infinitely exact. When you're looking at standard scientific notation, explicitly whatever digits you see here, that's a significant digit. So this has 2, and this has 4. bet this calculator does the power of 10. But the way I would do this is multiply. If I'm just doing these values times, that's essentially what I'm doing. The moles cancel, the grams of argon ends up over here. I would just multiply this by this and see what I get. 9.2 times 39.95. Turn it on. 9.2 times 39 point. Sorry, backspace. No, 9.2 times 39.95. I might have to go use my phone for as long as it lasts. Enter. All right. My calculator says, now I'm going to tack this back on, because I didn't involve that. So that's still there. Significant figures wise, there's 2 there, there's 4 there. I'm really just keeping those 2. The 7 goes around the 6. So and this does show 2 significant figures because there's not a decimal there. If you wanted this in standard scientific notation, we've got 10 to the negative 4 now. It would be either of these is correct numerically. If you put a decimal there, that shows 3 significant figures. But that's 2. And this is in standard scientific notation. So now if I finish this out, I will say, I'll do 3.7 times 10 to the negative 2 grams of argon. That's correct. And grams of argon. That's also correct. Even this is correct. It's 10 to the negative 4, 1, 2, 3,